Okay, so now we're ready for the derivative. And the derivative is what's going to drive most of what we do the rest of the year. So, getting this down and understanding what's going on here is going to be pretty crucial. So if you don't get it the first day, we're going to keep hitting it for quite a while. So, be ready. Here we go. Talking about the derivative. We're going to look at the formal definition today and also at the tangent line problem. The derivative is just the formula for the slope of a tangent line of a curve for any point on that curve, whether we're given that specified x value or not. We can find the slope of any curve. We can find the slope of the line very easy. We did that in Algebra 1, where we would take y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Real easy for a line, because it's linear. When we deal with curves, it's not so easy to find the slope of that, which is why we use the derivative. Now when we talk about a tangent line, we talked about tangents before, I think. We had, let me get a little template here. We had maybe a circle, and then we looked at a line tangent to the circle. It maybe intersected the circle at one point, kind of like that. Okay, so we did that before. Or maybe it intersects it. Oops. Maybe it intersects it at one spot, maybe like that. Okay, so now we're looking at curves, where I might have a curve that looks like this, and I could have different tangent lines. I could have a line tangent to it maybe right there, or I could have a line tangent to it, if I can draw another one, maybe right there, or I could have a line tangent to it, could be maybe like over here. These are all different tangent lines, where they just intersected at one spot. Just come along and touch it. Now, when we dealt with the circle problem before, we said that it would touch it at one point and it wouldn't go through. Tangent lines can go through, just kind of depends on where it's oriented. Let's see if I can get another one here. I want to move this one around. So maybe this one's tangent right there at about, a point that's maybe right here. These are all different tangent lines. They just come up and they just barely touch the graph. Okay, so some notation. First of all, when we're talking about the derivative, if I want to find, say, the derivative of, if I want to find the derivative of f of x, okay, the derivative of that looks like this. F with a little tick mark here of x. That's supposed to be a parenthesis. That's called f prime of x. That's how we say that, f prime of x. If I want to find the derivative of y, sometime we'll usually see it this way. And what does this mean? Well, this means, and this is kind of the way we read it, we say dy dx, but what it means is this is the derivative of y with respect to x. Okay, sometimes we'll just look at it like that, y prime, just like the f prime. Another way, if I want to take the derivative of f of x, it might be written this way. The derivative with respect of x to x of f of x, like that. The derivative with respect to x of f of x. And then once in a while, this book will show, I've not really seen it anywhere else like this before, but it looks looks kind of like this. A big D with a subscript x and then of y or f of x, whatever the case may be. So that's just a notation. Make sure you know what this means. Again, this is f prime of x. This is y prime. This is dy dx. It just stands for the derivative. Okay, now derivative, we said the derivative is the slope of a tangent line to a curve. So let's look at a curve. Let's just say I have, I don't know, some curve here. Let's call it, I don't even know what, but some curve. Okay? Now here's where the formula is derived from. If you don't understand what I'm about to say here, that's fine. We'll be talking about it later. But just to give you an idea what we're looking at. So say I want to find a curve, a tangent curve. So say I have this tangent line here, and I want to find the slope of this tangent line at this point right here, because this is the point where it's tangent. I want to find the slope of this line, where it's tangent to the curve right here. Now, if I had 2 points on this line, I could find the slope of that line using my slope formula. But I don't have 2 points. I only have 1 point. This is the only point I know. So the way the derivative is developed, if you will, we're going to find a different line. So I need to pick another point on my curve. Say right here. Now if I have 2 points on this curve, I can draw a line through these 2 points. Maybe I can, maybe I can't. Something like that. Gosh, I don't like this tool. It doesn't do what I want it to do because I can't rotate this. Well, I'm just going to call it right there then. And I'm going to have it go through this point and let's say this point. So ignore this point I drew over here. If it'll let me. And I can't erase that right now. Oh goodness. Okay, well, if I have 2 points on a line, I can find the slope of this. So this has an x value here, and then over here it's going to have my f of x value, where this is the ordered pair x, f of x. I got my x and my y. Okay, and then what's going to happen is I'm going to go through a change in x this way, horizontally, delta x. Okay, and so where I end up over here, well, this ends up being the value x plus delta x, because I'm at x here, and I add delta x to it. This is my change in x. So this is my x value, which means up here along the y, this is the value f of x plus delta x. And so what we're going to do is, if I can find the slope of that line, then I can end up finding the slope of the tangent line. I'm going to shrink this down a little bit. Okay, so if I want to find the slope of that blue line, well, that slope is going to be, I would take my change in y, this is my change in y, these are my 2 different y values. I got my y sub 2 minus my y sub 1 over my x sub 2 minus x sub 1. And my x sub 2 in this case is x plus delta x minus x sub 1 is just x. And so what happens is these two on the bottom end up canceling out, this x and this minus x. So I just have f plus delta x minus f of x on top over delta x, f of x plus delta x. So now the problem is this blue line I've got over here, that doesn't approximate this tangent line very well at all. But if I were to move my value here, if I move my value of x along the curve closer and closer and closer to this desired point, well, what happens is as I move it closer along this way, my delta x keeps getting smaller and smaller and smaller. So if I were to have it at this point I had here, or maybe I have it here, or maybe I have it here, as my x value gets closer and closer to this spot right here, well, my tangent line keeps leveling out and approximating this black line we're looking for. And so what happens is, what's going on is my delta x, since it's getting smaller and smaller and smaller, it's approaching 0. And so we end up with our formula for the derivative. So here's our definition of the derivative of f at x. And you're just going to have to memorize this, okay? So the derivative, or f prime of x, is the limit as that delta x approaches 0 of f of x plus delta x minus f of x over delta x. And then we just treat it like a limit. Now, you might be able to tell, if I just take it from here in this general form and plug in 0 for delta x with my direct substitution, I'm going to end up with 0 over 0. Okay, so as you're finding these limits, we've got to do whatever we can algebraically to make sure that this delta x can get canceled out and go away, because we don't want it to be 0. Otherwise we end up with something undefined, and that's no good. Okay, so let's try an example. Here's our formula again. So we're going to find the derivative of this function here, this parabola, f of x equals x squared. And when we're done with that, we're going to use the derivative to find the equation of the tangent line at this point 1, 1. This point is on the curve. When x is 1, 1 squared is also 1. So this point 1, 1 is on this parabola. We're going to find the equation of the tangent line. Remember, the derivative is the slope of the tangent line. Always remember that. Derivative, slope of the tangent line. Okay, great. So let's find this derivative. So this derivative is going to be the limit as delta x approaches 0 of, well, I'm going to go back up here. I've got f of x plus delta x. So I'm going to plug in. Okay, I'm going to put x plus delta x into my function. So instead of x squared, I'm going to use x plus delta x squared. And then minus f of x. So I'm going to subtract. So this is this part here. This part here, I'm going to subtract f of x. So I'm going to subtract, my f of x is x squared. And then it's all over delta x. Okay, again, I can't just plug in delta x here, 0 for delta x, because I'm going to end up, it's going to go away, 0 over 0. Don't want that, so we're going to have to do some algebra here to take care of this. Well, let's go ahead and multiply. Let's go ahead and expand this binomial here. Now, this is more than just common mistake alert. this is more than just x squared plus delta x squared. Remember, delta x we're just going to treat it like another variable. But this is a binomial, so when I square that out, if I FOIL that, I'm going to have x squared. I'm going to have a middle term of 2x delta x, and then plus delta x squared. Then I'm going to subtract the x squared on top over the delta x. Okay, all I did there, if you're following along, all I did was expand this binomial. This minus x squared is still here, the delta x is still on bottom. This right here is going to be the square of that binomial. That's some Algebra 1, Algebra 2 stuff. Okay, so next step, well, let's look for any common terms I can take care of on the top. Hopefully you see those. What can we simplify there? Well, I've got an x squared here and a minus x squared over here. So these are going to cancel out. And I'm going to be left with, well, I've got 2x delta x plus delta x squared on the top all over delta x. Let me get myself some more room here. Okay, now what can I do? Well, look at the top. Numerator, I think I can factor out a delta x on top. If I factor out a delta x, I get 2x plus another delta x. And this is all over delta x. Okay, so now that I have that common factor of delta x, I can cancel it. Now, I'm not worried about dividing by 0. Now I can go ahead and do my direct substitution here. If I plug in 0 for my delta x, I'm going to end up with final answer 2x. Okay, so 2x, so for this function, f prime, or the derivative of f, is equal to 2x. Okay, but they asked us to do something else. Second part of the equation. The question says, find the equation of the tangent line at the point 1, 1. Okay, so we said that the derivative is the slope of the tangent line. So, if the derivative, or if the slope is equal to the derivative, well, at this particular point I'm looking for, right here at the point 1, 1, well, I'm going to plug in, since the x is 1, I'm going to plug that in, excuse me, I'm going to plug that in over here into my derivative. So if I plug that in, f prime of 1 is going to be 2 times x, x is 1. So my derivative at that point is 2. If the derivative is 2, then the slope of the tangent line is 2 at that point, at that x value of 1. This right here, the 2x, that's the general form. That's going to give me the slope, or that's the derivative at any particular point. It equals 2 when x is 1 value. So if I ever want to find the derivative, or if I want to find the slope, find your derivative, and you can plug in any x value here, any x value it asks for. So now we can just use our, if you remember your point slope form, equation of a line, it's going to be y minus y sub 1, the y value is 1 at this point, and equals m, which is the slope, times x minus x sub 1. The x value is also 1. So I got the x value of 1 here, I got the y value of 1 here, I got the slope here. The point slope form. And I can leave it in that form if I want. Let's try another example. Let's find the derivative of this. Y equals 4x cubed minus 3x squared. Okay, so again, we're going to use our formula. We're going to look for the limit as delta x approaches 0 of, in this case, it's going to be 4 times x plus delta x, quantity cubed. Everywhere I see an x, okay, remember your function notation. Everywhere you see an x, you're going to plug in x plus delta x. Then I'm going to subtract 3 times x plus delta x squared. And then minus f of x. So minus, well, my f of x is 4x cubed minus 3x squared. And it's going to be all over delta x. Okay, so take a minute to expand that. Multiply this all out. Multiply this out. See what you can combine on the top. And get to cancel out. And then see if you can factor out a delta x so we can get rid of this down here. So expanding that out should look something like this. 4 times, this here is going to be x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed minus 3 times this binomial again, x squared plus 2x delta x plus delta x squared minus our f of x all over there. Okay, now let's get some like terms. Let's distribute and get some like terms together. Okay, so after we distribute, hopefully you can see this, we've got 4x cubed plus 12x squared delta x plus 12x delta x squared plus 4 delta x cubed minus, distribute this 3x squared minus 6x delta x minus 3 delta x squared, and then subtract these two terms, so minus 4x cubed plus 3x squared all over delta x. So now we look for any like terms we can get rid of. Well, I see a positive 4x cubed here and a minus 4x cubed over here. What else? Anything else alike? Well, we've got a minus 3x squared here and a plus 3x squared here. So now if you look, all the terms we have left have a delta x term in them. And so now if we want, well, we can factor it out, and then we can cancel it with this delta x or just divide it, but let's go ahead and factor it out so you see it here. So if I take out a delta x now out of everything on the top, I'll be left with a 12x squared plus 12x delta x, because I take 1 out, plus 4 delta x squared, factored one of those out. Then I have a minus 6x, took out the delta x, minus 3, another delta x, and then that's it, all over delta x. Now, well, I've got this delta x here and on top and bottom that I can cancel out. Now, I can just do my direct substitution. Everywhere I see it, oops, everywhere I see a delta x, I can plug in 0. So this term here will go to 0. This term here will go to 0. This term here will go to 0. So all I'm left with is the 12x squared and the minus 6x. So the derivative the y prime, if you will, or dy dx. Don't know what I'm trying to write. Should have had that all along here. This is dy dx. dy dx equals, so dy dx equals 12x squared minus 6x. One more thing to consider. When we take the derivative, or when we derive a function, we say it's differentiable. These are all same vocabulary. I mean, different vocabulary words all mean the same thing. If a function is differentiable, it means we can take the derivative. Okay? And differentiability implies continuity, but not the other way around. So that means if you can find the derivative of a function, or if we say a function is differentiable, then it's always continuous. If you can always get the derivative, then it's always continuous. Now, there may be places where you can find the derivative, but it's not continuous. You might be able to find the derivative on a certain interval, but if it's differentiable on the entire function, then it's going to be continuous on that function. But it doesn't go the other way. Some functions that are continuous may have a derivative that does not exist at a certain point. You might have a derivative at other places, but not necessarily. And here are two cases where that's true. If we have a curve that has a vertical tangent line, so say we have something that's coming along like this, this is fine, I can take the derivative here. But if it curves up and goes vertical for a little bit and then comes back around like that, it's not differentiable in here. Even though the function's continuous, wherever we have a vertical tangent line, I'd have a tangent line that's vertical right in here. Go right through, tangent to it right there. So that's no good. Can't find the derivative at that point. I can find the derivative elsewhere on the function, but not right there. So this function is not differentiable at that point, even though it is still continuous. Other places, when we have sharp curves, like say the absolute value function. Absolute value function comes down, goes back up, it's a V. Okay, we have a sharp curve right here, a sharp point. And the reason you can't find the derivative there is because, well, let's think about this. Remember, the derivative, by definition, is a limit. Well, if I'm looking for the derivative at this point, the limit, or the derivative this way as I'm approaching this point from the left, is a negative, has a negative slope. Remember, the derivative is the slope of the tangent line. Whereas on the other side, this has a positive slope. As I approach it from the right, the slope is positive. So these aren't going to have the same value, the same limit, the same derivative as I approach this point from the left and the right. So this derivative does not exist at this particular point. I can find it elsewhere on the curve, but not there. Okay, so give that a try. There was a lot here. We'll work on these in class, but see if you can do a few of these on your own this weekend. And, well, there you go. That's the derivative.